Need to track how many tokens your dspy programs use across multiple language model calls. You'll see how to enable token usage tracking for a simple program that chains 2 AI calls together, then retrieves the complete token statistics from the final output.
Import dspy. Hash configure dspy with tracking enabled. Dspy configure. lm equals dspy. lm OpenAI/GPT-4o mini cache equals false. Track usage equals true. Hash define a simple program that makes multiple LM calls. Class my program, dspy.Module. Def in itself. Self predict 1 equals dspy, chain of thought, question answer. Self predict 2 equals dspy, chain of thought, question answer score. Def call self question SDR. Answer equals self. Predict 1 question equals question. Score equals self. Predict 2 question equals question. Answer equals answer. Return score. Hash run the program and check usage. Program equals my program. Output equals program. Question equals what is the capital of France? Print output. Get LM usage.
This demonstrates composable LM programming, where individual prompting strategies are encapsulated as reusable modules within a larger workflow. The code shows how dspy modules like chain of thought can be combined into a parent program while maintaining clean separation of concerns. The key distinction is treating LM interactions as modular components rather than monolithic prompt strings. The pattern works by defining self-contained modules that handle specific tasks, then composing them into sequential pipelines. Each module manages its own LM calls internally while exposing only the inputs and outputs declared in its signature. The framework automatically tracks aggregate token usage across all module calls when configured, providing program-level observability without manual instrumentation. This approach matters because it brings software engineering principles to prompt development. By structuring LM interactions as composable modules, you gain reusability and maintainability for complex workflows. The usage tracking shown here gives you visibility into total token consumption for the entire program, which is essential for cost monitoring in production systems. Let's break it down.
Import dspy.
This imports dspy, the core library for defining structured language model programs. It provides the base classes like module and chain of thought that we'll use to compose LM calls.
Dspy configure. lm equals dspy. lm OpenAI/GPT-4o mini cache equals false.
This configures dspy to use OpenAI's GPT-4o mini model as its language model backend. The cache equals false parameter ensures each prediction generates a fresh API call rather than potentially reusing cached responses.
Class my program, dspy.Module. Def in itself. Self predict 1 equals dspy, chain of thought, question answer. Self predict 2 equals dspy, chain of thought, question answer score.
This creates a custom dspy module combining 2 chain of thought predictors. Predict 1 generates answers from questions, while Predict 2 scores the question-answer pair. The class structures a sequential reasoning workflow where evaluation depends on prior generation.
Program equals my program. Output equals program, question equals, what is the capital of France?
Instantiates the myProgram module and executes it with the test question. This runs the full workflow, generating an answer via Predict 1, then scoring it with Predict 2, with the final result stored in output. The next line, not shown here, will retrieve the aggregate LM usage metrics for this entire execution.
Print output, get LM usage.
This prints the total language model usage statistics after running the program. The getLM usage method returns aggregate token counts, showing the combined cost of both LM calls in the pipeline. dspy.Module composition. The code shows how to build a dspy program by initializing predictors in init and chaining their execution in call, where one predictor's output feeds into the next. Token usage tracking is enabled through track usage equals true and accessed via getLM usage on the program's output. Custom modules let you group related predictors into reusable components with explicit data flow.
The module that forgets its steps remembers the path.